Very good afternoon, ladies and gentlemen. My name is Abhishek Chaudhary, and I'm from Panshul Technologies. Thank you for taking out your precious time today for this webinar. And the agenda for our webinar is on SolidWorks simulation. So I believe most of you are already coming from a background of SolidWorks CAD. So today we will be giving you an overview on what are the various capabilities on the simulation aspect, that is the CAE, CFD, and the plastics part of the SolidWorks. So the agenda of the webinar is the what is the need of simulation in the design and development, simulation capabilities of SolidWorks. We'll go through some motion analysis case studies, static structural, and Q&A followed by a quiz which will have a Amazon gift voucher of 500 rupees for the winner. So I would request everyone to stay till the end so that you get a chance to win the exciting prize. So in this webinar today, we would be mostly focusing only on the static structural part because we have a lot of depth when we talk about SolidWorks simulation. So we'll see what are there in the motion analysis, static structural, and we'll exclude some thermal and CFD part, on which we will have another session probably in the coming days. So about myself, I'm an elite application engineer in 2023. My name is Abhishek Chaudhary. I am leading the technical department of Panshul Technologies since past 6 years. I have a collective experience of 12 years, and I have been in this channel for last 6 years, implemented more than 200 plus licenses of SolidWorks simulation and PLM solutions of Dassault systems. So now coming to the main agenda, like what is the basic need of simulation? So in the traditional process, which we are already habitual to, we create a 3D model, we build a physical prototype out of it, and then we test the performance. If the performance is not good, we go to the iteration again. We create the 3D model, that is we modify it, we again build a prototype, and then we again test it. So due to this, a lot of iterations get created and also the development cycle gets increased. So how to squeeze this? So that's why there comes a need of simulation for better process. So first we would create a 3D, then we build a virtual prototype wherein we test all the movements or the motion or the mechanics. And then we extract the whatever the loads or the forces are acting, we extract it and then simulate the performance in our simulation software. Once validated, we optimize the design in the 3D directly. So we bypass this production. There's a prototyping, that is the physically creating each and every iteration. So the number of physical iteration gets drastically reduced, which ultimately yields to the less production cost or less development cost, and also gives our technology an edge to the competitors, and that we are basically validating our designs before we go to the manufacturing stage. So you can streamline your development process. So preliminary, whatever like we had in the design stage, every stage comes one after one. That is the preliminary project and concept. Then the mechanical and electrical design used to happen. Then the design validation happens. Then technical communication is done. Then the operations. Now with SolidWorks, we can have all these things integrated seamlessly, and they can work in a parallel manner. So your electrical and mechanical design can work seamlessly using SolidWorks 3D CAD and SolidWorks Electrical. Similar in the similar time phase when the development is going on, you can continue with the design validation part also and technical communication also. At last, what you are reducing the timeline, which ultimately saves a lot of money. So what is the impact of SolidWorks simulation? It is innovation. So for product innovation, we need tools which can squeeze the project cost or the product cost and also save our time. So with SolidWorks simulation, you get a quality and performance increase, time and cost reduction. So this is what we promise with our portfolio of solutions. So what's included in SolidWorks simulation? So SolidWorks Simulation is a powerful, intuitive, and robust tool which is completely integrated with the SolidWorks 3D CAD, and it is coupled with simulation capabilities. Under SolidWorks Simulation FEA, we have a complete product simulation solution which includes motion, that is kinematics and dynamics, then plastics. So you can test the plastic part, like where is the warpage, how much time it will take to cool down. And then we also have our CFD capabilities. Inside CFD, you can have the flow simulation of air, gases, and liquids. In the FEA part that we would be focusing today, majorly comes the static structural and the non-linear part of the simulation. So what is SolidWorks Simulation? SolidWorks Simulation is a fully integrated FEA tool with SolidWorks, which enables virtual testing of parts and assemblies. Originally, it was known as Cosmos Works. Now it is known as SolidWorks Simulation, since it is it now comes under the SolidWorks brand portfolio. Based on it is completely based on the FEA principles that we have all read and understood in the engineering part of our education. So what are the capabilities of SolidWorks simulation? So we have three portfolios, three flavors: standard, professional, and premium. As you might be able to see on the screen, inside the standard we can do static. Static means body at rest and the force is constantly applied. Fatigue analysis, motion analysis, and trend tracker. So with trend tracker, you will be able to move between multiple iterations seamlessly. Inside SolidWorks Simulation Professional, we have optimization, thermal study, frequency study. Then you also get a material web portal, which includes a lot of data of the tested material, like the SN curves of the materials. You can get it from there. Then event-based motion analysis, it is there with SolidWorks Simulation Professional. Pressure vessel simulation, then edge weld connectors, buckling, drop test analysis, like anything that falls or while lifting your machine. Just in the worst case, it gets unhooked from the lifter. Then how it will impact it, that you can test it. And then 2D simplification for symmetric models, subdivision modeling, and then load case manager. Inside the SolidWorks Simulation Premium, you get non-linear analysis, like for hyperelastic materials like rubber. Dynamic analysis, as well as dynamic fatigue and composite analysis, where the materials have multiple layers, like carbon fiber kind of thing. So we'll start with the very basics. So this is the motion analysis. So motion analysis is something that is integrated with SolidWorks. So I'll start with a sample. So let's say I understand that most of you might be from different companies. So our agenda today is to basically enclose whatever we can show in a quick duration of 45 minutes. So this is a conveyor. So in this, basically, let's say we created a motion assembly, motion inside this assembly, where you can see a part is being moved forward, and then it is getting lifted using this mechanism, and then it is transferred in the forward direction, right? So you can simulate such kind of things inside the SolidWorks motion using the motion analysis thing, and then whatever the loads on these particular pins are coming, right, that can be seen in form of graphs like this. So now let's say I want to validate there is a connector. So this is the conveyor connector. Okay, I want to validate like if this can sustain the load or not. So what we did initially, we run the motion analysis, and while it is picking up, you can see these are the graphs. Now we have extracted it from here. You can see the maximum force on this connection 4 is like around 1900 newtons. Okay, so which is the connection 4. You can just select it, like go to edit here, and you see that this is a connection 4 on this pin. Basically there is a load of 1980 or 1900 newtons approximately. So now what we can do is, now we need to validate like if this can sustain or not. So we quickly created uh, a configuration out of it, and then we created a simulation study. So now inside SolidWorks, you can see that simulation is a part of the SolidWorks interface itself. So you need not jump between multiple softwares whenever you are just thinking about to do some FE analysis. So you can directly go, and I just kept this much as the required assembly or required part, whichever I want to validate. So this is my focus area. Now I have the loads. So first we need to give the fixtures. So we have added a fixture on these two particular faces, that these cannot move in radial direction, and these are locked basically. So fixture defines, since our model is into the 3D space, we have to define like how this model is being holded, or it is fixed in the real environment. So to define that, we added some fixtures and gave these values to the fixtures, and added these normal faces as the constraints. And when I clicked on OK, it got added. Okay, now the next thing is we define force. So to define force, there are multiple parameters we can define. We can define force, torque, pressure, gravity, centrifugal force, bearing loads, and lot many other features inside this static part. Okay, so here we have already predefined the force that we got from our analysis, and we converted into an x and y direction since it was a resultant force. So we extracted an x and y direction value out of it, and then we applied the same inside this holes. Okay, then you need to quickly create a mesh. So inside mesh we have an option you can have multiple types of mesh parameters, like blended curvature based mesh. Wherever there is fillets or cylindrical faces, we can define a blended curvature based mesh, and then you can define a maximum and a minimum size of your mesh element. So these elements are nothing but the node to node difference between two nodes is the element. So the higher the number of elements, the more accurate it would be, but then more the time it would take to run the analysis. So as you can see now, I have made the meshing. Now we need to define the material. So to define the material, I can just right click on any of this part here, and then we can define, apply edit material. We in SolidWorks we have a whole list of material library, for different categories of steel, iron, aluminum alloys, copper, titanium, and all. And if required, you can also use our SolidWorks materials web portal, wherein you will find more details on the materials if you don't find it inside our material database of SolidWorks. Also, we can create your own set of database so that you can use them again and again in case there is any special grade steel. So as you can see that when I run, it gives me result in form of stress. So this stress result shows me that the maximum von Mises stress is around 44.413 mm. Okay, which is comparatively very small if we compare to yield strength of steel. Also, even the displacement part, I can see that this is the displacement. You can have an animation out of it. Like this is how this is going to act. The force is going to act. So this is on a very micro level scenario. It is just to understand like how the forces are getting extracted. Also then we can use our design in our design can be basically optimized using the using this checker. Okay, so in this will take some time, so I'll just skip it. With this checker, basically you can reduce the weight of the material, or you can also double click here and then you can change the desired value seamlessly, let's say 1.25, and then update it. And once you update it, and you can rerun this analysis and check if the results have modified, and what is the deflection between the previous and the current result. So likewise, you can save a lot of material. Ultimately, saving material can save the cost of the cost for the company. Now, jumping back to our presentation. So static study, it checks for the stress and displacement for performance and quality check to avoid failure, decrease over dimensioning, increase the mechanical resistance on the part and assemblies by checking the factor of safety calculation, evaluate design changes to change the product quality. Now we'll have some more examples on static structural part. Before we move that on that, I already created a case for you. So you can see like there are three chairs here. Okay, so these are the tools. Some of them have ribs, some of them have a depth, much deeper ribs, and one of them doesn't have any rib. Okay, so when we run this analysis, we get three cases wherein no ribs, shallow ribs, and deep ribs. We found the factor of safety of 1.37, 1.49, and 3.8. So ultimately, considering that we should save some material as well as some cost for the company, also not compensate on the factor of safety part, we selected this 1.5 as the correct one, as the go ahead one, because you can see that the cost per million to manufacture this stool was about 1.233 millions. Okay, and the same for the shallow ribs is 1.328 million, which is approximate 8%. So with an additional 8% amount of the cost, we get an increased safety. Also, the customer would have trust on the component that it would not fail, or it would not break, or it would not get ruptured. Okay. So now we'll jump to some more studies inside the SolidWorks. So I'll show you some live examples on that. Really sorry on that. Okay. Now let's say some of our machines, okay, they have boltings. So with SolidWorks simulation, you can test the boltings, like if those bolts, whatever you have selected, are accurate or not. So to do that, you can just go to new study, click on static, and click on OK. Okay. So this with this, the static study gets created. Then I need to add some pictures. To add the pictures, I'll just go to picture manager, or I can go to fixed geometry and then select this bottom joint as the fixed geometry. And then to add the holes here, or the bolts here, we have connections. So whenever there are bolts or pins, you can use such connectors like pin connector, bolt connector, bearing connector, spot weld, edge weld, linkage rod, or links and springs can be simulated and tested. So we'll go to bolt, and then you can select the two edges where this bolt is going to get fit. Okay, so one is the outer and one is the inner. So you also need to define the type of the bolt, like what type, what it is. If it is a counter bore, or if it is a counter sink, if it is a threaded one. So we give a threaded one here, and also you need to define the material out of it. Then you need to define some strength data. So if you know the tensile strength data or threads per mm, let's say 2 threads per mm. Sorry, 0.8. Okay, and then what should be the expected factor of safety, so that when it gives you the result, it shows in color that it is green. If it is 2.5 or 2.1, it will give you a red if it's 1 or 1.5. Okay, then we need to define the preloading condition, that is at what torque this bolt was fitted. Okay, when you give these values to this particular thing and click on OK, then you'll be able to see the bolt connector, something like this. I'll just show some connectors quickly. So you can see that these are the some pre-made connectors I already added. Once these connectors are added, then we define interaction. So wherever there are two solid bodies touching each other, we define contact, that these are in contact with each other. The one is the one is the housing, and second is the channel, is the square tube. Okay, and once this is defined, and then you need to define the force. So currently that is around 200 kgs, that is around 2000 newtons approximately, in a normal direction. So normal direction is straight and the downward direction. After that, we quickly create a mesh. Once meshing is done, then we are good to go for the simulation part, and we can just click on this run study. So SolidWorks also plots a convergence plot automatically, and it reaches a point of convergence, and then only the solver gets stopped. While doing this study, if you ever see some disruptions here, like a lot of ups and downs, you can understand that the study might get failed. It could fail because of some fixture problems, or probably due to some contact issues, and then basically you can solve those contacts or issues again, and then rerun this. So this convergence plot is something that it should always go in the downward direction like this. Okay. So once this convergence plot is done, we will be able to see the result again in form of stress, strain, and displacement. And along with that, we also get something called as the pin bolt check. So we'll just wait for a couple of seconds more. So meanwhile, I'll just open some existing models which we already completed. That I can give you a gist of how the failure looks like. So, just a second. So this was for a three bolt bracket. So we completed this study. So to show you how the result looks like, you can see that when I show the pin bolt check, it shows me the bolt connector is in red. It is currently showing me that the calculated factor of safety is 1.44 for this one, 1.45 for the connector 2, and 1.34 for the connector 3. So our desired factor of safety was 2. That's why it's currently showing in red color. So this way, basically, you can identify like which parts or which boards can fail, and also then you can first we selected for the 3 boards, and then we replaced it using the uh, 4 bolt bracket, and we change the shape of the bracket as well. So once this will run, I'll show you the result. Yeah. So we have the result. So when we check this, so here we can see that the calculated FOS is 1.9, still far better than what we did initially. The second one is 1.8, the third one is 1.89, and the fourth one is 1.8. So considering that, we can basically say that this is quite safe, because it almost reaches the our desired factor of safety, that is around 2. Or you can basically change the size of the bolt also. So this is how it looks in case when the force is when the load is applied on the bolt. Also, you can see that there is a stress on this plate, since because of the axial loading or the torque loading of the bolt tightening. So you can see the bolt tightening effect has been added here inside the SolidWorks simulation. Right. So now moving on to the next topic of the static structural part, I have one more part. So in this, many of us are into machine design, and our machines are bolted using the foundation bolt. So just like a normal bolting, we also have a foundation bolt option. So here you can see that there is a foundation bolt option. So using the foundation bolt, the method of selection is the same, we just need to select a face, an edge, as well as a plane. So this plane acts as the ground plane. So this plane acts as the ground plane, and then you need to define the properties of the bolt like that, like initially we defined. Based on that, it will again give you results in terms of stress. So you can see that the maximum stress is around 15 MPa. The pin bolt check, it shows me that there is no I think there is no issues on that. We'll define pin bolt check also. Okay. So need attention 0. So when you select details, you get the loads on all the bolts. So you also get a detailed the forces that are acting on that bolt group. Symmetrically also we can solve this. So what we did is we basically removed one section, and then we added a vertical mid section rib here, and then we added this bolt, and once we run it, we get the similar results. So what happened is basically we here there were two plates initially. Now there is only one plate which is added at the center, so which reduce the weight of the object, right? And when you show the bolt check, it also shows that none needs attention. That means it is safe. Also we can extract some plot detail information, like let's say you want to probe or you want to check like what is the stress on this particular point. So you can go on selected entities, place on this line, and then click on update. Okay, this can be also viewed in form of a curve, that on this particular edge the maximum and what is the maximum stress that is acting, that is around 12.5, I guess, right? So with this plot tools, basically you will be able to plot a lot of additional features, and which you can use it in form of report. So reports can be again extracted using just by clicking on this report. SolidWorks will automatically include all the information from the model, and it will also include the snaps of these stresses, displacement, strain, and pin bolt check. And then when you click on apply, it will create a automatic Word format report. Now moving on to the next part. So some of you might be into EV segment or bike segment. So we can also test the chassis of bikes, or wherever there are structural components. So what we did is that to reduce the number of time, to reduce the simulation time, we converted the whole chassis into a surface body. So surface body is a zero thickness body, which ultimately gives you a lighter. That is, the mesh would be a 2D mesh and not a three-dimensional mesh, due to which the simulation runtime will drastically get reduced. So in this, you can see that all these bodies are surface bodies. I have applied a 1050 material on this. So once the material is applied, then we defined a global interaction, that these are all bonded with each other. So I defined bonded. So bonded is nothing but telling the software that these are welded with each other, right? You can see that these are the welding grooves that we have made, and you can see that very nicely inside the simulation. Okay, and then we added fixtures. So fixture is to tell like how this is getting support, or from where it is fixed. So these are the edges that we have given as a fixed geometries, and then we create a mesh. So previously you saw that with that simple component also it took a lot of time to mesh, but now we have a complex geometry, still it meshed like within a couple of seconds. Also you can see that there is no thickness. So this thickness is basically defined using the thickness manager. That is, you need to define, go here, right click, and edit. That is a shell manager. So inside the shell manager, you can define thicknesses to multiple surface bodies. So here you can see that these are the thicknesses that I have already added it for you. And once these thicknesses are added, then you can go and run the study. So you'll be able to see that much faster result you'll be able to see. So now you can see that the maximum yield strength that this frame can handle or the material can handle is 27.57, and the maximum one miss is that it is that it is loaded with is the 52. Now where this is 52 MPa loading happening, we can just go on this edit definition. We can go to chart option. We can show maximum and show minimum value. So here you can see that the maximum is at this particular point. So this is the area from where basically the rupture can happen or the failure can initiate. Uh, Also, you can see the displacement. So to make it more readable one, I'll just make it to floating. So you can see that there is a displacement of 0.79 mm. So happening something like this, right? You can plot a factor of safety plot, which shows that that these are the areas which are below factor of safety limits of 3. So our upper factor of safety limit is 3, and the minimum factor of safety, you can see that it is around 0.15. So here there is a definite chance of failure from this particular point. Also, we defined some weld check plots which shows the welding colors, that these are the weld connectors, so it needs attention. Also, you can see that it also shows in red and green color. So these are the weldings which can basically fail due to this load. So this is that. So this is the welding which can fail, and another one from where the failure can happen in these two areas. So you need to, so what are okay? So these are the okay welding connectors. So this is how basically you can quickly evaluate how this how to check the safety of a product when it is welded, when it is having some structural component, or we can also define this welding things from here, like edge weld. All you need to do is just go to edge weld and then select the faces, phase 1, phase 2, and then give the intersecting edge a selection, and then define the electrode type and the under the hook lifting devices, if any, estimated weld sizes. You need to put it here and click on OK. So like that, you will be able to define the welding thing. But to define the weld connector, you will have to have SolidWorks simulation professional capability with you, right? Now moving on to next thing, next simulation, that is the storage tank. So this is a storage tank. We want to check that when an earthquake comes, okay, how this tank structure, or what is the acceleration, that is the G value, which is under which this structure is getting exposed to. To start with, we start with simple new study, and then we go to static study. Inside static study, we have already created a lightweight version of this. As you can see that these are all, this is completely hollow, and also this is a surface body. Just as I previously said, like to save the time of our simulation, we can basically create a lightweight models of our objects, and then we define some pressure, that is since this is our tank, so we give a pressure, and so this is the pressure value that has been added. Okay, the fixture, so fixture are the bottom faces, and then we just dry run it as it is. So once you run it, you get the result in a static condition. That under static condition, what is the result? So remember, static study would be the very first thing that we always check in any kind of simulation inside SolidWorks. So with static study, you can basically now copy this study and then move to different type, like static, non-linear, inside non-linear, non-linear static, or non-linear dynamic. So that capability would be there, or linear dynamic. Under linear dynamics, let's say you want to do earthquake analysis, then it would be a random vibration or a response spectrum analysis. So static study is something that is the foundation of all kind of simulation inside SolidWorks. Next thing, I want to have a transient way. Let's say I want to check it for about 25 different frequencies. Okay, so for to do that, basically what we did is we created a transient study, that is from the static study only. We just copied it, go to static linear, and then select on this model time history. Okay, so we created a transient study out of it. Inside this transient study, we need to define the base excitation. So base excitation is an external load. So with some accelerometers, it is now possible to define like what is the x or y coordinate of the earthquake. So these are basically time. So for a period of let's say we tested it for a period of 31 seconds, and this is the amplitude of the accelerometer that so this gets multiplied with the g value, so which we are putting it here, right? So this is the through accelerometers we can have this kind of curves, and we can import it, and we can click on OK. So once you do that, you get results like that. So you can see now the 1 Mc stress has drastically increased, showing much more realistic value due to seismic response, that is a seismic earthquake. So you can see that the object is also vibrating in such a manner that it is getting some vibrations, and then it is getting deflected. So if I just slow it down, probably you will be able to understand in a much better way. So still, the yield strength of material was 351, as you can see at the bottom right hand side here in the plot, and the maximum 1 Vc stress that we are having here is 350. So it is quite closer to our yield strength. And what is this location? These are basically the foods or the support members, right? What is the displacement? So displacement is around 57 mm, happening at the top part, something like this. And also we can see the acceleration values also at how many g it is getting, at different steps. So we can have an animation. So, the maximum g force acting on this body due to the earthquake is 1.132. So similarly, we can plot a response spectrum analysis also. The process is same for response spectrum analysis as well. The only difference is here you get more information out of it, like the g value, as well as what is the at what acceleration, like meter per at 11.734 meter per second square. This particular body is getting oscillated due to the vibration part of the earthquake. So this is how basically we can quickly run some response spectrum analysis and test and use the static simulation as the base study of almost all the simulations. Now we move to some structural component. Like many of our machines have some weldment components, that is the square tubes, C channels, I beams, right? So how to test them? So this is a typical example of a jib crane. Okay, let's say I want to evaluate this, like how this structure of this jib crane will act when the load is completely acting in the downward direction, or when the lifting is getting happened. So we can go to this static study. Okay, and then inside static study you can see that these are the points. So this is a smart software. It automatically understands that these are the connection points between the two members, beams or columns. So these are the yellow ones are the endpoints, and the pink one are the joints. So it automatically understands that. Then you need to define the connections. Global interaction, I defined it as a bonded. These are welded with each other. It can be contact if these are basically in contact with each other, or if these are welded, these are bolted. Then we defined a a fixed face, which is our holes. Okay, and also we defined a roller slider. So just to simulate that this is the ground plane, and the bolt are basically getting locked here. So instead of giving a bolt connector here, because I don't want to check the foundation bolt here, I want to validate the structural capability of this object. So I gave this fixed and roller slider option here. Then we defined load in terms of force, which is defined on this particular face acting downwards on this joint actually, on downwards at around 3000 newtons. Okay, and once you run it, it gives you result again in form of stress, strain, and displacement. But now, uh, now see, now this is a member that is a fabricated member. So SolidWorks bifurcates between a fabricated member and a welded geometry. So inside this fabricated member, the maximum 1 BC stress is 32, and in the structural member, the maximum stress is around axial bending moment is around 14.2. Okay, so it automatically bifurcates between the structural components and the fabricated components. Okay, and gives you a consolidated view. The maximum displacement is around 20 mm acting downwards, obviously. So you can see that the maximum displacement is happening here. And also many of us are like in the previous days I have received many queries like how to plot an bending moment SFD BFD plots. So that also can be plotted here using the defined beam diagrams, and then you need to select the beam on which you want to plot and then select on OK. So you get this plot like this, and then this chart can be tweaked a bit like this. Okay, so this gives us a and this gives us a beam diagram. So this is how you can quickly evaluate the beam diagrams. You can check the factor of safety as well. So when you show the factor of safety, we can see that the minimum factor of safety of this jib crane is around 0.83. So which can basically probably lead to a failure. So what we can do, we need to evaluate like what is that area. So to do that, I can go to right click here on this factor of safety plot, go to ISO clipping, and I want to see the values which is below 1 actually, below 1 reverse. So below 1, so you can see that almost. So some parts of here like 1.5. So this is the area from where the failures can happen, not at the bottom one. So at the top part, this is the area from where the rupture can happen. So this iso clipping, you can see that this is in red color, right? So which has a minimum minimum FOS size 0.843. So the failure can initiate from this point, and it can probably lead to a breakdown of this jib crane. So to solve this, obviously we need to increase the plate thickness or change the material, like as you want to do. Like you will have to add some weight, or you can basically change the material out of it. So I think I have covered most of the structural part. Apart from the structural simulation, we also have flow simulation capabilities. As I was previously speaking to you, that today, due to some time constraints, I think we won't be able to cover all aspects of our simulation capabilities. But we did cover the static simulation. Inside flow simulation, we have internal and external flow analysis, heat transfer analysis, or then flow analysis of rotating components like like centrifuge and all those things, impellers. Then some external analysis like due to wind acting on a windmill can be tested. Then compressible and non-Newtonian liquids can also be tested here. Laminar and turbulent situations can be tested. and also time dependent CFD analysis can be done. Apart from that, we also have capabilities of doing some electrical CFD like joule heating or the typical like PC and laptop analysis, wherein we test the heat sink, then the printed circuit board analysis, thermoelectric coolers, etc. Inside this HVAC simulation, so these two are add-ins which work over flow simulation capability. Inside HVAC, you can test the comfort parameter of a room if you are into design of clean room equipment or clean room. Probably comfort parameter is something you would be looking for. So with the comfort parameter, you get to know that what is the ambient temperature that the room has to maintain, or if it's able to maintain or not, what is the highest temperature, like that. Apart from the flow simulation, we also have more detailed capabilities, which include SolidWorks plastics. Again, in plastics, we have standard, professional, and premium. In standard, you can do these are basically for the plastic simulations for the core cavity, for the mold, for the person who are into mold designs. So it competes directly with Autodesk mold flow, and it comes at a very cheaper rate as compared to the mold flow. So I think that's all from my side. Now, Rushikesh, I'll ask my team member to kindly share the quiz for the day.
Thank you, Abhishek. I'm sharing the quiz QR. Guys, you have to answer these questions. You have a time of 2 to 3 minutes, so you have to answer these questions. Let me share this screen. Internet option. No.
Please hold on for a couple of minutes. I'll share the link for the quiz. Hey guys, quiz is open. Please scan this code using your mobile camera and just quickly fill out uh, the right answers. I believe the session was fruitful and informative to every one of you, and you might have learned something new today. Now it's time to earn back something. So those who are unable to see or scan this image, you can also check the message window. We have also shared a link of the same in the message window. So I'll also do one more thing. So I am just allowing all users to ask questions. You can unmute yourself and then you can ask questions if you have any. So we are just giving access. You can ask your question after 1 minute. So we already have a winner, Bhagyesh Bhosle. So we already have a winner. The fastest to do this, I think, in 4 minutes, we received the answer. So congratulations, Bhagesh. You will get the coupon in your mail on which you have registered. That is Bhagesh Bhosle at 0@gmail.com. Also, our team will get in contact with you and confirm the same. Anyone who wants to ask particular questions, I am open to answer, open to your queries. You can ask your questions, and we'll be happy to answer you. And if not, thank you for giving your precious time today for the webinar, and stay connected. Hope to see you soon in our next webinar. Thank you.